Hi everybody! Do you remember the 3D tunnel created using a texture mapped onto the inside of a cylinder? I think the result looked quite decent, especially when the camera was set in motion, giving us the impression of flying through an endless tube that disappears into distant darkness. This time, let's try something similar, but without textures and with a triangular shape. So this time we don't have any background image, so I'll create a simple scene with a color rect, set the usual dimensions and add a new shader material. Let's do it. Right click on the scenes, create new scene, call it triangular, okay, and right click at child node, color rect, and for the color rect we'll set the usual dimensions, which should be 600 by 400, and the shader material in the material section. So new shader material, click new shader, triangular GD shader canvas item, and I'll put it to the shaders folder. Create and click again to open in the editor, and I'll expand this area a little bit. Very well, so we'll delete everything we don't need, leaving only the fragment function. The usual drill. Okay. Great. Now I'll create the usual skeleton where we shift the origin of coordinates to the center and adjust the aspect ratio. It is necessary. Otherwise, our equilateral triangle we could have seen at the beginning of the video would stretch horizontally and would definitely no longer be equilateral. So, uniform vector 2 resolution will be vector 2 600 by 400, just like our color rect, and at the fragment function, first shifting the origin of coordinates, vector uv is uv minus 0.5, and the aspect ratio uv.x is multiplied by resolution x divided by resolution y. Okay, to make writing the following code easier, we'll define a few constants, which I'll place below the uniform parameters. There will be 3 constants in total. First one, const float super simple. It is a good convention to write constants in capital letters, so that's why I do that, is 3. So why super simple? Supersampling is a method we'll use to smooth moving horizontal lines, and we've created something similar before in a tutorial for a movable 3D grid. In this case, all you need to know is that we'll be rendering triangles multiple times, very close to each other, to reduce the unpleasant flickering in the more distant parts of the effect. Okay, the second constant, const float, angle sine, would be square root of 3 divided by 2. So what is this? As we know, the internal angle of an equilateral triangle is 60 degrees, and since we'll need the sine of this angle in several places, it's worth pre-computing it in this form. We know that sine of 60 degrees is exactly a square root or half of square root of 3. Okay, and the final one, const float triangular step, which would be 2 divided by 3. The last constant will be used to distribute the horizontal lines, which we want to nicely follow the individual sides of the triangle. Later, we can use various multiplies of this constant to create denser or sparse line patterns for the tunnel. So to render the basic shape of the tunnel, we'll also need to calculate the triangles on which the entire effect is based. We'll do this using the following method, where we'll use one of the constants and compute the side edges using the dot product. It is a standard formula that you can find in many other shaders. So I'll put it here and call it float equilateral triangle with an input parameter vector 2p for the current point, and will return max of py and max, I will just put it to another line to make it better readable, dot product of p and vector 2. Now we need the sine of 60 degrees and negative 0.5, and the second parameter is another dot product, code complete, another dot product of p and vec2 negative angle sine and again negative 0.5. Okay, yeah, this could be correct. I'll just fix the brackets. Is it correct? Yeah, perfect. And one more thing will be useful. We'll add a uniform parameter for the color of the final effect. I'll do it here. Uniform, like 3, the RGB color, 3 components, line color, with a hint source color for the color picker in the inspector, and the default value, let's set to 1. We want a green triangle, and 0.5. Okay, I think you can see it here in shader parameters. Nice, shining green color. Very well, and now we'll finally improve the fragment function. First, I will write the code, then I will explain it. Okay, let's scroll down to the fragment function and write these lines. We need some result which will act as an accumulator, and at the end we will use it for the final color. And now the super sampling. So next line. For float x from 0 to the super sample constant and x plus plus. This is the first cycle, and the second one for float y from 0 again and again to the super sample constant value y plus plus, and now the cycle itself. So we'll define the p point, which is basically the UV coordinates, but increased by the super sample shift. So it will be vector 2, x minus 1, and y minus 1, which means we'll get values negative 1, 0, 1, as long as the value is 3. Otherwise, we would have to do some small changes. Anyway, now the triangle. Float triangle is the result of our function equilateral triangle with the parameter p. And the final color would be fract of triangle, which will ensure some kind of periodical effect, as we'll soon see. And finally, the result would be increased by clamped value, because we want to keep it in the range from 0 to 1. Color 0, 1. All right. And finally, result must be normalized. So we divide it by the super sample to the power of 2. Supersample times supersample. And let's assign the color, which is vector 4. So that would be vector 3 of the result and 1. No, not yet. The line color. So we want to color the triangle. And 1. Let's wait. Okay, we have some equilateral triangles here, definitely, but the result is still far from resembling a tunnel. So we'll improve everything step by step. But first, let me explain what we've actually written in the code. Okay, so the double loop x and y ensures that we render our object a total of 9 times 3 by 3 according to the supersample constant, each time with an offset based on the vector added in the definition of P. That's exactly what I said just a while ago. Then we get a triangle, and to limit it to the visible part of the screen, we use the frac function on the resulting value. Finally, we add the obtained value to the result variable to the accumulator, which we divide by 9 after the loops to normalize the sum of the individual layers, and then we render the pixel multiplied by the set color. Obviously, there is too large a gap between the layers, so we'll introduce a uniform parameter blur, which we'll use to control this factor. And to make it easier to adjust in the inspector, we'll use its value divided by 100 in the calculation. So let's do it right like this. Uniform float blur and range, and set it to 0.2, and the range would be from 0 to 1 and 0.01 as the step. And let's modify the vector 2 definition. Scroll down to the fragment function, and the vector p is here. So we have this, and now we need to multiply that by the blur value. As we can see, it is still pretty big, so dividing by 100 means multiplying by 0.01. That's a bit better, and we can see a hint of the future tunnel. However, it's necessary for the triangles to repeat at the correct spacing for this type of 3D rendering. Let's make a simple adjustment to the definition of float color. So, where is it? Here, float color is a frac triangle, and instead we'll use the inverse value. 1 divided the triangle. Now that's something. We have our first rough tunnel. There are still plenty of details to improve, but at least we've hinted at the direction we'll be taking. The next step will be to get rid of the gradients so that we are left with just the lines. The step function is best suited for this. We'll add this line after definition of the color. So we'll add this simple line. Color is step function applied on color and the edge of 0.1. Wait for it. Great. However, it would be even better if we could get rid of that grainy chaos in the middle of the tunnel. In the texture tunnel tutorial, we did the same thing, and now we'll use the same approach. First, I will add a uniform parameter tunnel fade. Right here, uniform float tunnel fade with a range, and the initial value would be 2, and I'll make it from 1 to 10, for example, and the usual step. Okay, and we'll improve the end of the fragment function. Just like in the previous tutorial, we'll use the pow function for the power. So we'll calculate the shading, which is the maximum in the center, and gradually decreases towards the edges. And finally, we'll multiply the resulting color by this new variable called dist. So let's find it here after the result. Let's define float. Dist is power of length UV, len. Sorry about that. Still getting used to the new keyboard and tunnel fight as the exponent. And the color multiplied by line color and multiplied by dist. Wait for it. Okay, a nice result. It will be even more impressive once we animate the entire tunnel. Of course, the next step is to create horizontal lines indicating the tunnel walls, for which we'll first add a uniform parameter for their thickness. I'll put it here, uniform float line thickness, hint range, and the initial thickness would be 5. And let's make it from 0.1 to 10 and 0.01. So to keep the code readable, I'll implement the tunnel walls in a separate function. I'll write it first and then explain it as usual. So let's put it after the equilateral triangle. Float tunnel lines will have the parameter vector2 p, just like the previous one. Okay, and now float angle is a tan, which suggests the polar coordinates, as you may have guessed, and py divided by pi, because we are working on the full circle. And now float color would start at 0, and we need to do this. Float line starts from -1, -1 to +1, and this time the step won't be just 1, but our triangular step multiplied by 0.1. So we have more horizontal lines. And in this cycle, color is increased by the result of step, angle, and line plus line thickness multiplied by 0.001, because the thickness is still too high and we just want the horizontal line to be as thick as the triangular ones. So this is the first, and we need 2 of them because we'll be limiting the pattern on both sides. So 1 minus step angle line, this time minus line thickness, and again multiplied by 0.001 and semicolon. Okay, and finally we can return the color value. Return color. Okay, so what do we have here? The variable angle contains the direction of the line in polar coordinates, which is very suitable for our purpose because we want to draw lines from the center in all directions. And since a circle has a period of 360 degrees, we need to divide the angle by multiples of pi. This is in this case. And again, to avoid getting circular segments as a result, we need to limit the calculation using the step function. This time, there are 2 such functions because we want the restriction on both sides. Okay, and now we can add the result to the fragment function. I'll find it here. So we have the double cycle and yeah, here to the color. So color is increased by the tunnel lines. Tunnel lines of P and semicolon. And of course, equals is missing here. Let's add it and wait for it. Great. I would say we are almost done. There is one more detail that may not be very visible, so I'll show it a bit enlarged. It's the vertical line in the center of the top part of the screen. Let me shift and enlarge. Now it should be clear. Do you see it too? The line doesn't seem to pass exactly through the vertices of the triangles. Here, and so on, because it's missing its right half. This is because the used interval from -1 to 1 ends exactly at this point and doesn't extend into the next circle. We can easily fix this by expanding the interval a very little bit. I think 1.1 should be sufficient. Let's try it. And wait. Great. I would say it is fine. But we want the tunnel to move, right? Let's add the last two uniform parameters, which we'll use to control the forward flight speed and rotation. I'll just revert to the original zoom factor, 100%. Okay, so uniform parameters right here. Uniform float forward speed, hint range, and initial value 2, for instance. It will be from 0, so we can simulate a full stop to 10 and step 0.01. And the second one, uniform float rotation speed. Again with a hint range and the initial value this time 0.1. So it doesn't rotate too much. And from 0 to 1, sure. Okay, and we'll use them in the fragment function as usual. First, the forward movement, for which we just need to slightly adjust the definition of the color. Where do we have it? Here. So it's fract1 divided by triangle, and let's increase it by time multiplied by forward speed. Here. Okay, the tunnel is moving now. If we want to stop it, let's simply set the forward speed to 0. Where do we have it? Here. It is set. Let's reset. Okay, now for the rotation. We'll need the usual formula for calculating the 2D rotation matrix. I will add it, I think, here to the top. Right after the constants, so mat2 rotate of the angle alpha, or A, float A, and now, just like we did before, nothing new is here, sine A, float CA is cosine of A, and we return the matrix 2 by 2, which consists of two vectors, CA, SA, and the second one is negative SA and CA. Okay, and I'll add another line to the fragment function, just here after the aspect ratio recalculation, so the UV would be multiplied by the result of the rotation matrix, and that's it. Rotation matrix time times this time rotation speed. Rotation speed, semicolon, wait. Okay, now we are completely done. The tunnel slowly rotates while the camera flies forward. In the inspector, we can again adjust both speeds, set the line thickness, increase or decrease the shading at the center, and change the color of the entire effect. Thank you for watching. There are surely games where a similar tunnel could find its use, and even if not, it's always good to know how to render an equilateral triangle in repeating layers within a shader, or how to simulate sidewalls using polar coordinates. So take care, and I'll see you again in the next video.